Dear student, myself Srinivas H. HOD, Department of Physics, Government Postgraduate College, Chikbalapur. In this session, now we shall discuss about what is the relation between Peltier coefficient and EMF. We know that what is a Peltier coefficient? The amount of heat, energy absorbed or evolved at one of the junction of a thermocouple when 1 coulomb of charge flows across the junction is called Peltier coefficient. It is denoted by pi. So, the amount of heat energy liberated or emitted, liberated or absorbed, capital H is directly proportional to charge. Charge can be written as current into time. Current into time. This is a required expression. Now remove the proportionality. There is introduce a proportional constant is a pi. So pi is the Peltier coefficient. Call it as equation 1. H is equals to pi I t. Call it as equation 1. If V is the amount of contact potential difference at the junction, then amount of heat can be written as H is equals to E of I into T. So this is called it as equation 2. Now observing equation 1 and 2, we get pi it equals to EIT. IT get a cancelled in both LHS and RHS. Remaining pi equals to E means Peltier coefficient equals to EMF developed at a junction. This is the relation between Peltier coefficient and EMF. In next slide, so we say has conclude hence the Peltier coefficient at a junction is numerically equal to the contact potential difference at the junction. Now let pi 1 and pi 2 be the Peltier EMFs developed at the junctions. Then thermo EMF total EMF capital E equals to phi 2 minus pi 1, where pi 2 means thermo EMF at a junction 2, pi 1 is thermo EMF at a junction 1. So it is nothing but what is the pi? Pi is equals to, pi can be written as here pi equals to T into capital T. This is a general relation, capital T into dE by dt. Capital D dE by d theta. dE by d theta. So here missing pi equals to T. This is the capital T thermodynamic temperature into dE by d theta. T is the temperature at the junction. dE by d theta is nothing but thermoelectric power. It is denoted by P. Pi equals to Tp only. Pi equals to, simply we can write as T into P. What is the P here? dE by d theta. That is thermoelectric power, where T is absolute temperature and dE by d theta is a thermoelectric power. It can be represented by capital P also. Now comparing Peltier effect with Carnot's heat engine. What is the Carnot heat engine expression? Q1 by theta 1 equals to Q2 by theta 2. So here Q1 and Q2 are the heat energy at source and sink only. Similarly, theta 1 and theta 2 are the temperatures at source and sink. So this is a very familiar equation. By using this equation in the similar way, we should write theta 2 by theta 1 equals to pi 2 by pi 1. Theta 2 by theta 1 equals to pi 2 by pi 1. So this equation is held or deduced from the Carnot heat engine. Theta 2 by theta 1 equals to pi 2 by pi 1. Next we shall move next. So now add up both the side minus 1. So what happened here? Theta 2 by theta 1 minus 1. Here pi 2 by pi 1. Here, this is a pi 1. Pi 1 minus of 1. Now take a LCM. Here LCM, LHS side, LCM is theta 1. Okay. Theta 2 minus of theta 1. Okay. Next in RHS, what is the LCM? Pi 1. This is a pi 1 denominator minus of pi 2 minus of pi 1. So it can pi 2 minus, now deduce the expression for pi 2 minus pi 1. So pi 2 minus pi 1 retain in LHS side and remaining all right in RHS. So pi 1 by theta 1 and theta 2 minus of theta 1. So here pi 2 minus pi 1 can be written as dE or d pi. dE is nothing but d pi. Okay. You people having an idea, dE is nothing but d pi. So pi 1 is nothing but pi. Theta 2 minus theta 1 can be written as d theta. Theta 1 can be written as in generalized theta. So this is the one of the relation. D equals to pi times of d theta by theta. So now relation is drawn for pi. So what is the relation drawn for pi? Pi is equals to, by using this equation, pi can be theta into d theta by pi is equals to theta into dE by d theta. So this is the derivation or meaning. What is the required expression to the pi? The required expression to the pi equals to theta into dE by d theta. Theta is nothing but thermodynamic temperature at a junction. dE by d theta equals to thermoelectric power. Thermoelectric power. That's all. This is very important in the point of the examination for 8 marks. Next slide. Inversion temperature. What is the inversion temperature? You know that already I explained in last class only. Inversion temperature is a temperature of hot junction at which the direction of EMF just changes. The EMF direction is a changes. So just to recall the graph now, EMF versus theta along the x-axis, the graph found like that only. So this is a neutral temperature here, Tn. So this is inversion temperature, T high. So here the curve should be reversed, means the direction of the curve should be reversed. So here EMF is equals to 0 at inversion temperature. So therefore what is the T high? T high equals to minus of A divided by B. This is a required expression for inversion temperature. Recall here T high or theta I minus A by B. What are A and B? A and B are Seebeck coefficients or thermoelectric coefficient. So this is very important for 2 marks question or 2 marks problem. They given a data of A and B, find out the inversion temperature. Next to neutral temperature. How to define neutral temperature? It is the temperature of the hot junction of the thermocouple at which the thermo EMF is maximum. So what is the relation? Tn equals to minus of Tn is equals to minus of A over 2B. A over 2B. This is the relation for neutral temperature. And what is the relation between neutral temperature and inversion temperature? Neutral temperature, inversion temperature is equals to 2 times of neutral temperature. This is very, very important. Neutral inversion temperature is equals to 2 times of neutral temperature, or neutral temperature equals to half of the inversion temperature. So this is very, very important. They are asking for 4 marks question. Calculate the neutral temperature and inversion temperature. If you know the A and B, then calculate the both Ti and Tn. Next we shall move. Next slide. Law of thermoelectric effects. So we having a two laws. They are law of intermediate metal. What is the statement of this one? If the junction of the thermocouple is opened and a third metal is inserted, the EMF for the couple AB remains the same. That is, without introducing C, provided both the junction of the third metal C are at the same temperature. So what is the meaning? Now consider two metals A and B having a thermocouple. So now check the EMF and temperature difference across A and B. That is nothing but same. Now introducing the one more metal, that is a C in between A and B. Now check the EMF, not at all change. If introducing third one, there is no change of the EMF. This is the law of thermoelectric, law of intermediate metal. Next, second one. Law of intermediate or successive temperatures. According to this statement, the EMF for thermocouple between temperatures T1 and T2 is equal to the sum of EMFs for a number of successive steps into which the given range of temperatures may be divided thus. So, what is the meaning of this statement? The EMF for thermocouple between temperature T1 and T2 means any two temperatures. The EMF between any two consecutive temperatures is equals to the sum, algebraic sum of EMFs for a number of successive steps into which the given range of a temperatures. So now let's see of here. What is the EMF between the, if temperature T1 and T power n, in between T1 and T5. I want to, how many, what is it total EMF between at a temperature T1 and at a temperature T power n. So that is nothing but E. E is nothing but total EMF at a temperature T1 to at a inside the bracket square. T is missing, just we understood or consider a T only. So to fill the T inside the square bracket, T1 T power n. This is a total EMF between the temperature T1 and T to the power of n. This is equals to the how many steps? 1, 2, 3, 4 up to n minus of 1 to T to the power of n steps are considered. Means this is one of the EMF. 1 you summing, adding the all these steps of the EMF is equals to the total EMF E T1 power E T power n. So this is the meaning of the law of intermediate or successive temperatures. Next we shall move the Thomson's effect. What is the Thomson effect and how Thomson effect is working and how animation diagrams are drawn. Let's see in a next slide. Thomson suggested that when a current flows through unequally heated conductors, heat energy is absorbed or evolved throughout the body of the metal. This is nothing but statement made by Thomson. Positive Thomson effect. Diagram shows copper B at C is the center point. At a point C heated, the current flow from A to B. Here M and N are 2 points found at a same distance from C and which shows to the same temperature. When a current flow from A to B, so here N at a N shows higher temperature than M. At a point B shows higher temperature than A. So here observe here the AC across AC horn heat is observed, across CB heat is evolved. This is nothing but positive Thomson effect. Similar effect showed by antimony, silver, zinc and cadmium. So now the direction of the current changes. What happened here? When the current is passed from B to A, M will show higher temperature as compared to N. Next, negative Thomson effect. So now take a iron bar heated at a center point C. The current direction flow from A to B. At a point M shows higher temperature than N. At a point the A higher temperature than B and AC shows to the heat is evolved. At CB shows to the heat is absorbed. This is nothing but negative Thomson effect. Similar effect showed by a metals like a platinum, bismuth, cobalt, nickel and mercury. Next, now consider a lead bar. It is heated at a point C. So here also M and N 2 points are placed at equal distance from C and shows to the same temperature. When here current flow from A to B, there is no change the temperature at M and N. Therefore, in this case of a lead, Thomson effect is nil. Due to this reason, lead is used as one of the metals to form a thermocouple with other metals for the purpose of drawing the current. Thomson coefficient. The amount of heat energy absorbed or evolved when 1 ampere current flows per 1 second in a metal between 2 points which differ in temperature by 1 degree centigrade is called Thomson coefficient. It is denoted by sigma. Its unit is volt per degree centigrade.